Welcome to CS Course Companion. Have you ever faced a problem so complex, so massive, that finding the absolute best solution feels impossible? Well, you're in exactly the right place. Today, we're jumping beyond the classic search methods to look at two really powerful AI algorithms designed for just that. Let's get into it. I want you to imagine this for a second. You're trying to find the highest peak on a mountain range, but you're surrounded by a thick, dense fog. You can only see a few feet in any direction. You have no map, no compass, and you can't even remember the path you just took. That is the kind of problem we're talking about today. And honestly, it's the perfect way to think about our first algorithm. So here's the game plan. First, we're going to break down a really simple, intuitive strategy called hill climbing. Then we're going to expose its one major fatal flaw. And finally, we'll see how a super clever technique, inspired by blacksmithing of all things, called simulated annealing, swoops in to save the day. Okay, first things first, we need to get one thing straight. We're not talking about your standard search algorithms here, like A-star or breadth first search. With those, the goal was always about finding the best path to the end. But here, we couldn't care less about the path. All we want is that one single optimal final state. Think about designing a computer chip or creating a university timetable. You don't care how you got there, you just want the final layout to be perfect. And this whole idea is what we call local search. The core concept is actually super simple. You just start somewhere, look at your immediate neighbors, and take a small step to make your situation a little bit better. And get this, because you only ever care about your current state, these algorithms are incredibly efficient with memory. So let's go back to that foggy mountain problem. What's your gut instinct? What would you do? You'd probably just always take a step uphill, right? Wherever you are, just find the steepest way up and go. Well, that simple, greedy idea is exactly what hill climbing is all about. And the algorithm itself is just beautifully straightforward. I mean, look at this. Step 1, plop yourself down at a totally random spot. Step 2, look around at all the places you can get to in one step. Step 3, move to whichever one is the highest or the best. And step 4, you just keep doing that over and over again. Step up, step up, step up, until you reach a point where every single direction is downhill. At that point, you just stop and say, well, I must be at the top. But it sounds a little too easy, doesn't it? And yeah, you've probably already guessed the problem. There is a huge, inevitable flaw in this greedy strategy. What if the peak you just found isn't the real peak? This image just says it all. Our little algorithm starts climbing, it feels great, it's making progress, and then it reaches this local maximum. From its perspective, it's at the summit. Every direction from here is downhill. So it stops. It gets stuck. It has absolutely no way of knowing that the true highest point, the global maximum, is just across that valley. Let's make this more concrete with the classic 8 queens problem. Your goal is to get 8 queens on a chessboard so that none of them are attacking each other. A perfect board would have 0 attacking pairs, right? So we'll call that a score, or H of 0. Hill climbing might very quickly find this board state here with a score of H equals 1. That's pretty good. Only one pair of queens can attack each other. But here's the trap. From this specific position, any single move you could make would actually result in more attacking queens. It would make the board worse. So the algorithm sees no uphill moves and just gives up, stuck on a good but not perfect solution. So how in the world do we escape these traps? We clearly need a smarter way, something that can get itself out of these little valleys. And this is where our hero, Simulated Annealing, enters the scene. And right here, you can see the fundamental difference. Hill climbing is a pure greedy algorithm. It only ever moves to a better state. But simulated annealing, it introduces a totally radical idea. Sometimes to find the highest mountain, you have to be willing to walk downhill for a little while. It strategically allows itself to make bad moves. Now that name, annealing, is a huge clue. The whole concept is borrowed directly from metallurgy. When a blacksmith forges a sword, they heat the metal until it's glowing hot. This makes the atoms inside jiggle around randomly and chaotically. Then, by cooling it down very, very slowly, they allow those atoms to naturally settle into a perfect, low-energy, super strong crystal structure. We can steal this exact same idea for solving our search problems. Okay, that's a cool idea, but how does it work in practice? I mean, how does a computer algorithm decide when it's okay to take one of those seemingly bad downhill steps? Well, the secret sauce has 2 main ingredients: probability and this concept we call temperature. Check out this graph, it explains everything. At the very beginning of the search, the temperature is cranked way up. That's the top purple curve. This means the algorithm is wild and exploratory. It has a high chance of accepting pretty much any move, even a really bad one. It's just jumping all over the solution space. But as we run the algorithm, we slowly cool the system down. As the temperature drops, the algorithm gets a lot pickier. The probability of it accepting a bad move gets lower and lower until finally, when it's almost cold, it behaves just like our old friend hill climbing, only making good moves to zero in on the best solution it's found.
Okay, let's zoom out for a second and put all of this together.
This ball on terrain example is the absolute perfect way to visualize it. Think of hill climbing as just a plain old marble. If you let it go, it's going to roll down and get stuck in the very first dip it finds. That's your local optimum. But simulated annealing? That's like a super bouncy ball that's been heated up. It starts with so much energy that it can easily bounce out of those shallow valleys and keep exploring the whole terrain until it finally cools down and settles into the absolute lowest point, the global optimum. The difference is night and day.
So here are the key takeaways you really need to know. Hill climbing is fast and simple, but it's greedy and gets fooled easily by local optima. Simulated annealing is the much smarter solution because it fixes this problem by sometimes accepting worse states, allowing it to escape those traps. And this whole process is controlled by that clever temperature parameter that goes down over time. And this isn't just theory. This stuff is used to solve massive, real-world optimization problems. Everything from scheduling airline flights to designing the very computer chips in the device you're watching this on.
And that's our look at hill climbing versus simulated annealing. If this explainer helped things click for you, please do us a huge favor and hit that subscribe button for more CS Course Companion. We built this channel for you, so we really want to know, what's that one topic from your classes that's giving you a headache right now? Drop it in the comments below, and we just might break it down next. Thanks for watching, and I'll see you in the next one.